see. Oh. There's you guys. So
I can see what is that.
that says 78%.
Well, I'm pretty sure it says 88%.
So you guys did fall just short of the 80% margin. But if I average you with my other section and let the other section carry the weight for you guys, that kind of looks like 80%. So, yeah. I wanted to go through, first off, I just wanted to talk about one of the more difficult problems from the second exam, since, I think that a lot of people kind of whiffed on this, so I wanted to make sure we understood it, because I really liked this problem a lot, because I really thought it emphasized what I care about in terms of assumptions in this class, which, a lot of times we just kind of say, oh, whatever, assumptions are assumptions, we're just going to do it. But it's more important to me that we can look at a residuals plot and be able to interpret it correctly. We can look at it and be able to say something about what this actually means, how close our assumptions are to being satisfied, if such and such model fits assumptions better than other model or something like that. So I wanted to go through and talk through these and sort of justify why all of these had the answers that they did. Okay? So we'll just go through point by point. So the first problem that a lot of people had with this one had to do with a lot of people had trouble. A lot of people wanted to write A for B right here. Okay? And I think part of that was just you were seeing a lot of residuals plots, but this really isn't a residuals plot. If you see something like this, first off it says residual normal quantile plot. So normal quantile plot, that's a QQ plot. Okay? So we recognize it by the title, but even if I were to give you an unlabeled, I think that would be like a reasonable question on the test or whatever, is like give you a few plots and ask you, okay, which of these is a QQ plot? Or which of these indicates a normal distribution? And maybe like not all of them are actually QQ plots or something like that. So you should be able to recognize what does a QQ plot look like versus what does a residuals plot look like, right? So with a QQ plot, we've got our points are arranged in like an increasing order. They're following an increasing curve right here. Whereas with a residuals plot, things are going to look a lot more scattered. Okay? So that is a QQ plot, and that's why, so when you're looking at this residuals plot, okay, keep in mind what the residuals actually are. They're measuring how far above and how far below the line of best fit our data is. Okay, so if you look at the pattern for this guy, we've got a lot of points over here that are going to have positive residuals. They're above the line of best fit. Our line of best fit is underestimating those values. So we're going to have, remember the residuals measure the vertical deviations. Okay, so here, right, this point right here, we're going to have a positive residual. Okay? And so, whereas in the middle, we've got negative residuals. Okay? And then on the other end, we've got positive residuals again. So that's very consistent with this plot right here. Okay? And the issue that's highlighted by this residuals plot is one of nonlinearity. Okay, that was the assumption violated in this case. You might be saying, oh, well, it's a residuals plot. It's supposed to be telling us about homoscedasticity. It does tell us some things about homoscedasticity as well, but one of the benefits of residuals plot is they can highlight nonlinearity in a clear way. Okay? So that's why the correct plot for this guy was A. Okay? we might be trying to figure out why this QQ plot corresponded to this scatter plot right here. Okay, so this actually involves some a little bit of information from the previous exam, okay, which is that we're dealing with a positively skewed, and I wouldn't necessarily expect you to directly be, I kind of expected this to be the one that you, you sort of like, by process of elimination, you kind of solve this one or whatever. But you can justify it. We're dealing with a positively skewed distribution. Anytime we've got a QQ plot, right? So we should remember if we've got a QQ plot and it's curved, okay? It looks where it falls either, it's like concave up, okay? Or if it's concave down. Okay? Both of these are indicative of skew, but one of them is indicative of positive skew and one of them is indicative of negative skew. Okay? And the way that you can memorize, which one is positive skew and which one is negative skew. But I always like to think about why specifically is this shape? How do I justify to myself that this is positively skewed? And the real deal is that, well, what this line of best fit represents right here is that represents the normal distribution. Okay? So I'm looking at, ideally, the normal distribution right here. Okay? But that's not what happens. Okay? Instead, I'm going to have these values, and really it's better depicted on up here, but we see that we've got just a few values, we've got a few values that are too large. Okay? We've got high outliers, right? So that really indicates that we've got an upper tail. Those upper values are getting too big. So what happens here is we've got this tail. I'm going to have values that are too large over on the upper end. But on the lower end, what I see is my values don't get small enough. Okay? They don't follow. They kind of all collect together. Okay, right here. They don't follow the line of best fit. They just get cut off at a point. Okay? So the lower tail isn't small enough. It should be smaller or more negative, really. And so this is what the curve, the histogram, roughly, of the actual distribution will look like. Okay? And you could do the exact opposite thing to see why this is going to result in negatively skewed. A negatively skewed distribution. Okay? So, but this makes sense since we've got positive skew because I've got a bunch of values that are collecting on the lower end. Okay? That's where the bulk of the values is on the lower end, and then we've just got a few outliers that are out on the upper end. Okay? And so that's why B was the positively skewed distribution. It corresponded to that diagnostic plot. Okay? Cool. Let's see. E, I think this was one of the easier ones to figure out. Okay? This was, in both of these, you're going to be seeing, you're seeing fanning right here. The residuals plot just kind of does a better job of highlighting the fanning than the scatter plot does, but you can still see the fanning in the scatter plot. The other thing to recognize is you can really identify each point corresponds to a point over here. Right? You don't, I was a little bit afraid that this would be too easy, but because if you thought about it like you were just trying to match points up, then you can do that, right? So if you look at this point right here, okay, that's going to correspond exactly, right? You can see this is this large residual. That corresponds exactly to this point right here. You've got this second point up here. All that the residuals plot does is it kind of just it just kind of tilts. It doesn't quite tilt. It tilts and squishes a little bit our scatter plot. Okay, and so you can really just match points almost without thinking too much about what the scatter plots really mean. So you can see these 2 points up here, and those are corresponding exactly to the gap. You've got this bulk of points down here, you've got this bulk of points down here, and you can see these 2 points are sort of separated from the rest. So these scatter plots and the residuals plots are really, really intimately related to one another. Okay, so you should be able to find, even if you're not recognizing the main feature that I'm trying to point out in the scatter plot, you should at least be able to match some points and maybe make a decent guess. Okay, so then we've got, let's skip to scatter plot F right here, and this was looking at, okay, when you compared. Okay, what are the residuals doing right here? Well, in the middle, we've got lots of very small residuals. As we move outward, we're getting larger residuals. Okay, we can see that same exact behavior right in here. I've got very small residuals near the middle, and I'm getting larger residuals outward. And again, you can kind of match points together, right? I've got these like 4 points, 1, 2, 3, 4, that are following this kind of curve right here, and you can see those points again right in here. So there's a strong connection between these. Let's see. And then, so this was another violation of homoscedasticity. You're not really seeing the classic fanning, but it has to do with the inconsistency of the size of the errors. Okay, you're sort of seeing fanning in 2 different directions right here. Okay, you're seeing fanning outward from the middle. The errors in the middle are small, whereas the errors on the out, as we move away from the middle, our linear model becomes a worse and worse predictor for the response variable. Okay. Then the last 2 were 2 different plots where we didn't have any assumptions really violated. Okay. You looked at plots C, A and E right here. Both of them, they're not showing any kind of nonlinear patterns. They're not showing any kind of fanning, not any kind of funneling. There's nothing that looks too weird about either of these. And so it might be hard to determine which of these corresponds to which in terms of the remaining scatter plots. So we've got 2 different scatter plots remaining. Okay, that's F right here and C. And the key thing to identify is that our model is a really good fit for the scatter plot in C. We're going to have a really high R squared value that's going to be indicative of some small residuals. Okay, here we've got larger residuals. Okay, and so you can recognize I left the scale on here. You might not be able to see it super well on the overhead projector, but I left the scale right here. You can see that the residuals are much larger. They go from 0 to 10 on this plot, whereas they're going from 0 to 1.5. Keep in mind what the x-axis and the y-axis are corresponding to. The residual right here, this is, right, our y-axis is really our residuals, and the x-axis, these are our predicted values. Okay? And so that's maybe the best way of distinguishing between those. Okay. Definitely, I really like this question a lot. Expect to see some kind of variation of it. It's definitely not going to be exactly the same. Make sure you're familiar with how residual plots for ANOVA look compared to residual plots for regression. I think it would be one thing that I could do is do some kind of variation on this question, but for ANOVA instead. Okay, or multi-factor ANOVA, maybe with some interactions plots. I think that would be a good thing I could do. I could kind of try to get you to match p-values from an interactions hypothesis test to an interaction plot. Something like that, or maybe I just give you an interactions plot and say, okay, what do you think the p-value for this is? Okay, and you need to know, all right, how does the interactions plot relate to the p-values for the interactions hypothesis? Okay, what does that mean in terms of being maybe an additive model or not being an additive model? That would be a good variant on this. Another thing that I've sort of thought about doing, potentially on some previous exams, is like having a situation where you need to label or identify what the residual is in a residuals plot or in a scatter plot. I could, pick a point, give you a scatter plot maybe, pick a point and give you some labeled numerical values. And you've got to tell me based on the picture, what is the residual? Okay, what is the fitted value? Go through and identify there, make sure you understand, you have a good visual interpretation of what all of these things correspond to, okay? Just make sure you know how to read the pictures. Don't make sure that you understand things better than, oh, if it's a QQ plot, I want it to be straight if it's normal, and if it's not straight, then it's not normal. Okay? Yeah. Questions about picture problems like this? Yeah.
Will that be the extent that we need to know assumptions, or should we expect knowing all the assumptions elsewhere too?
I mean, so I'm not going to do anything like wildly different from the previous exams, right? The previous exams, I really didn't say like you need to go through and check your assumptions whenever you're executing a hypothesis test, right? What I was more concerned with was like, okay, here's a particular problem isolated from the rest where you need to understand assumptions. So I would make sure you're familiar with your assumptions. I'm never going to ask you a question that's like, go through and write down the list of assumptions and draw check marks next to them or whatever, like we do for group fun, because that's, I don't know, right? It's not super useful for an exam. Okay? Yeah?
I think you could draw like the ANOVA scatter plot and then like a correlating p-value.
Sure. Yeah, we can talk about what do our plots look like for ANOVA. Let me pull up some output from JMP. So they're really, when it comes to ANOVA, the plots we have a residuals plot and we have a interactions plot. And I just need to log into my Google Drive real quick. And that's it. We don't have to worry about a scatter plot. There's no real scatter plot for ANOVA. We do have box plots. That's the other thing actually that we can worry about. We can talk about a little bit is how the comparative box plots can look. Okay. So let me. So here's an example of a residuals plot, how a residuals plot is going to look when you've got ANOVA, right? It looks very different from the way that residuals plots look when we've got regression or simple linear or multiple regression, right? Instead of things looking just like a random pattern of dots, you tend to have like these stripes. You tend to have these vertical bands right here. And what we really care about with these vertical bands, the reason that this comes up is because each of these are individual treatments. So in this case, we had, this was the data set, this was the student attractiveness data set, right? And we had 6 different treatment conditions. There were 2, the experimental units were the graders, okay? And the graders could be provided 2 different essays, a good essay and a bad essay, and they could be provided with 3 different photos. So we had 6 different potential treatments, and what we're getting right here is the fitted values or predicted values for each of the individual treatments. I've got 6 different treatments right here. There are 6 different bands. You can't really distinguish 2 of them because they're right on top of each other right here. Okay? And what we want to identify when we're looking at this residuals plot is, so first off we want to say fanning versus funneling. Okay, is that going to be the case? And then with each of these treatments we want the level of variability to be similar. We want the size of the errors to be really similar. You don't want to have one of your treatments that's way more variable than the rest, that has way larger errors than the rest. Okay? And you don't want that's much smaller than the rest. Each of these like vertical bands should be roughly the same size as one another. So maybe I could provide you with a couple of different residuals plots from ANOVA, okay? And you would have to identify which of these violates homoscedasticity or something like that. That would be a good question. And then, so that's just in terms of assumptions that we could worry about. And then we've also got the interactions plot. Let me pull that up real quick. Okay. All right, and then the other thing that you should, I think that this one maybe isn't quite as clear cut as I would try to make it on an exam, but we've got some output from JUMP right here, and in particular we've got the p-value from the interaction hypothesis. So remember, this is testing the null hypothesis, that p-value of 0.4312 right there. Hopefully you guys can see it, but whatever this p-value is. Okay, that's testing the hypothesis the null hypothesis for the interaction between your factors A and B are gamma ij equal to 0 for all I and j. Okay? And if the null hypothesis for factor AB holds, okay, then we, an additive model fits the response. And make sure we're familiar with what an additive model actually is. Okay, an additive model, that's one where we don't have to worry about its xijk is equal to mu plus alpha I plus beta j plus epsilon ij. It's one where we don't have to worry ijk. We don't have to worry about an interaction term between our two factors right there. That's an additive model right there. If we reject the null hypothesis, for factor A and B, okay, we say there is evidence of interaction, or an interaction effect. Okay? And so how that would look when we're looking at plots, at least in terms of the interactions plot, is we should see, so we'll always get two different interactions plots, okay? They're just switching which factor we're putting on the x-axis and which we're plotting against separate lines. Okay, so they're equivalent to one another. But what we want to see is, in the ideal world, they'll be totally parallel. Okay, and probably they're going to look more, if I want there not to be interaction, I'm going to make them even more parallel than this on the exam. Okay? But in the real world, they're going to vary a little bit. Okay, in this case, some people were really concerned on the group fund with, we saw there's an intersection point between these two lines right here. It's not such a big deal. We've got a small difference right here. It's not surprising that we have a difference of 0 right there. They're not perfectly parallel to one another, but they're not necessarily always going to be perfectly parallel. But the important thing is they've got roughly similar slopes. Okay? They don't have dramatically different slopes. okay, and they're following this same pattern where the response, the score, is improving when we take the essay quality from poor to good. Okay? And similarly, when we look at how the response changes as I change the student attractiveness from attractive to control to unattractive, okay, we see, okay, there's moderate change when we move in both good and poor quality essays as I move from attractive to control, and there's maybe a more significant change as I move from control to unattractive. So we want to see that they're roughly parallel, but more importantly, we want to see that they're following the same pattern. It's when we get a situation where there's a lot of crossing, they're not following the same pattern, that's when we're concerned that there's going to be interaction. So this residuals plot is really consistent with this p-value of 0.43 right here. That would be fail to reject this null hypothesis right here. We don't have enough evidence to claim that an additive model does not hold. Okay? We can compare that to an interactions plot, okay, where we did see lots of interaction. Here we go. Okay. All right, here we've got an interactions plot where we're seeing a lot of crossing. Okay. We don't have consistency in terms of sort of what this was the finish treatment on these jackets, which one was best. Okay, in terms of like fire resistance or something like that. We're seeing differing patterns. Here, when we move from regular to soil, that treatment for one type of jacket, okay, there's improvement. For the other type of jacket, it's a negative effect right there. Okay, so that's evidence of interaction. We're not following the same pattern right here. If we removed this soil treatment right here, okay, then we would probably fail to reject the null hypothesis and say we didn't have evidence of interaction. Where we're seeing all the interaction is in this one treatment right here. And you can kind of see that in the other plot as well. Okay? Things would look pretty good if it weren't for this green line right here. They wouldn't look perfect, but they would look pretty good if it weren't for soil right there. That's really what's screwing things up. That's where we're seeing all the interaction effect. There's some sort of weird effect where that particular treatment just makes the structure of the jacket, it kind of reverses the relationship you would expect for the structure of the jacket and the flame retardants or whatever. And that's very consistent with what we see in terms of the p-value right here. Okay, we're seeing a p-value that's extremely small. Okay, so we would want to match that to an interactions plot where we saw a lot of evidence of interaction. There's lots of crossing, maybe skewness, that sort of thing. Okay, being able to understand these things on a qualitative level. I'm not going to ask you to look at an interactions plot and say, okay, what do you think the p-value is on this for this interactions plot, right? I certainly can't do that. But if you're given 2 or maybe 3 interactions plot, and I give you, the different p-values for each of them, hopefully you'll be able to match those. Okay, and that's really, for the most part, that's just like recognizing, okay, when do I have an additive model based on this picture, and when do I not? Okay. Let's see. The other we have. I'd say there were a couple of, I don't have any images or examples I can pull up right here, but there were there was certainly a problem in your notes that was like for a one-factor ANOVA experiment. We had two different pairs of box plots, okay? And we had like similar sample means. We had three different treatments. There was like treatment A, treatment B, and treatment C for each. But we were dealing with two different crops. It was like carrots and potatoes, okay? And we had the same averages for each of our treatments. Okay, so like the box plots were centered at the same values, but the data was like way more variable for one of the crops than the other. And so we should be able to understand, okay, even though the sample treatment means are the same, okay? If I'm looking at X bar, this